Okay, physics. I actually wasn't planning on doing, a video for physics today. I was just gonna let it be a study day. But I'm actually gonna make a video for two reasons. Number one, some people asked me some questions about numbers 21 to 23 on banked curves. So I wanna real quickly go over that. But number two, when I was going over the answers yesterday, for numbers 15 and 17, even I was stumped as to why they did the two questions that sounded the same, why they did them separately. And I probably spent, and I hate to admit this, guys, I'm so sorry. I probably spent a good hour and a half to 2 hours this morning trying to figure it out, and I was stumped. I couldn't figure out why what sounded like two identical questions were done two different ways. And I did Google searching, I watched YouTube videos, over and over and over again. I kept trying to figure this out until finally, after about the 15th time I read the two questions, I noticed the difference. So let me explain to you the difference, okay? In number 15, it says a boy is twirling a 155-gram ball on a 1.65 meter string in a horizontal circle. The string will break if the tension reaches 208 newtons. So I'm going to do that. I'm going to break this board up. I'm going to do that over here. So force of tension was 208 newtons, and the mass is 0.155. And I'm not going to spend a lot of time because I did this yesterday, but I need this for the explanation. 0.155, and the radius is 1.65. And the question was, what is the maximum speed? So I'm looking for a velocity. What is the maximum speed that you can twirl it before the string breaks? And when we figured that out, what we did was we did that centripetal force had to equal force of tension. And so the force of tension could be 208. And we did mass, which was 1.155 times v squared over r, which was 1.65, and we solved, and we got that the velocity was 47 meters per second. But in 17C, it said you have a stone that has a mass of 0.284 kilograms. And you twirl it at a constant speed of 12.4, it doesn't matter because that's not part of part C, in a vertical circle that has a radius of 0.850 meters. It says, what is the max speed that it can go if the tension, the max tension is 33.7 newtons. Well, that was not done well, sorry. 33.7 is what that is. And when we did this one, we actually did that centripetal force this time is equal to force of tension minus force of gravity. And so we solved it that way, saying the centripetal force is mass times velocity squared all over r, and that's equal to force of tension, which is 33.7, minus force of gravity, which is 2.84 times 9.81, and 9.81. And we solved for v, and it worked out to be 9.62. And when I looked at this yesterday and I was doing the video, one of the things that struck me, and I said, guys, I'm going to have to figure this out, is why in this question was centripetal force, equal to force of tension, but in this one it was equal to force of tension minus force of gravity. And I'll be honest, I didn't know. which I hate not knowing. I hate not being able to explain something. So like I said, I spent a significant amount of time until I finally read the question and I figured out what the problem was. And I have a handy dandy leash, because I happen to have a lot of those sitting around, to show you what the difference in the question is. All right, so in number 15, it says, a boy is twirling a 155-gram ball on a 1.65 meter string in a horizontal circle. That word horizontal is really important because it doesn't mean that he's doing this. Hopefully you can see that. It doesn't mean he's doing this. It means he's doing this. The circle's going this way. Well, that makes a difference, and here's why. If your circle is going horizontally, and it's really hard to draw horizontally, so I just drew a part of it, picture that being flat, like, picture it going this way, okay? Then the whole time, the center-seeking force, the centripetal force, is only provided by the force of tension in the string. Force of gravity, because force of tension is working towards the center of the circle, which is, I need 3 hands, which is horizontal. It's in this way. Force of gravity is working perpendicular to that. It's working vertical. So force of gravity has no effect on the centripetal force because they are perpendicular to one another. However, then when I read number 17, it said a stone is twirled at a constant speed in a vertical circle. So this time the circle's going this way, which means if the circle is going vertically, now gravity is playing a part. When it's at the top of the swing, gravity is going towards the center of the circle. Tension is going towards the center of the circle, so the two of them work together to provide that centripetal force. When the stone, or whatever it is at the bottom, force of tension is still working towards the center of the circle, but force of gravity is actually working downward. What that means is the maximum tension, the maximum amount of tension is actually, and the maximum velocity is actually going to happen at the bottom of the circle. Max tension and max velocity, I can't write, happens at the bottom of the circle. And again, if you think about it, it makes sense. Because when it's at the bottom, force of tension is pulling up, force of gravity is pulling down. So force of tension is having to not only provide the centripetal force, but it's having to work against gravity. So that's a lot for it to do. So that's where the most amount of tension happens, and the max velocity happens there. Because think about it, when it's going around, it slows down, it reaches its slowest point, and then as gravity helps in that circle, it starts pulling down. It's going to reach its maximum velocity when it's down at the bottom. Slow down, speed up. Slow down, speed up, right? So that's why here we had to subtract the two of them to get the maximum velocity that it can go, because that's where the maximum tension was happening. In a horizontal, the tension in a horizontal circle like this, I hope you can see that. I'm so coordinated. In a horizontal circle like this, then the tension is the same through the whole circular motion, because it's only tension that is keeping it going in that circular motion. Gravity's not really playing any part in keeping it going in that circular motion. So it all had to do with those two words, horizontal circle and vertical circle. That was the only difference between those two questions, but it made a huge difference in how you figure it out. And I am really embarrassed to tell you how long it took me to figure that out. So when you're sitting at home staring at your page, you're not the only one, okay? I have those moments as well, and I teach this stuff. All right, so that's that. So hopefully that makes sense. If it doesn't make sense, rewatch the video 2 or 3 times, I guess. I don't know. But that's really the difference there. And I tried to find a good YouTube video to explain that. There isn't one. They really don't talk about it too much. They talk about vertical circles and they talk about horizontal circles, but they don't talk about kind of the difference in how those work, which might be a good video to have. So, hey, maybe I've just invented a new video that actually has a purpose. I don't know. But that is what, and so, because I was going to put a link to somebody else's YouTube video and go, hey, watch this. Yeah, I couldn't find one. All right, so when I was going through different people's work on banked curves, some people asked for number 20. That was the most often asked for question, but I did that in the last video. So the next question, someone actually asked for 21, 22, and 23. It will be quick because they're not that long. So remember that for a banked curve, the formula that we're working with is tan theta is equal to not r, v. Why did I put r? V squared over r times g. So for number 21, it says a car exits a highway on a ramp and it's banked at 15 degrees. To the horizontal, the exit ramp has a radius curve of 65 meters. If the conditions are extremely icy and the driver cannot depend on any friction to help him make the turn, what speed should he travel so that he won't skid off the ramp? So really that's just a matter of tan of 15 is equal to v squared over 65 times 9.81. So make sure your calculator is in degrees and not in radians. If you were getting them wrong, that could potentially be a problem. But I would do tan of 15, multiply it by 65, multiply it by 9.81, and then take the square root of it because it is v squared. And again, maybe you were leaving off the squared in the question. That is very, very common. But it would be 13 meters per second. Now, if you were interested in knowing how fast that is in kilometers per hour, because we kind of think better that way, 13 meters per second, there are 1,000 meters in 1 kilometer, and there are 3,600 seconds in 1 hour. So 13 times 3,600 divided by 1,000, it's actually 46.8, so about 47 kilometers per hour. So if you were relying on just not friction, but on just the centripetal force, if you were relying just on the fact that they banked the curve so that some of your normal force went to keeping you on the road and you didn't need to rely on friction, then you should go under 50 kilometers an hour. Otherwise, you'll skid off that road. And I can tell you that going off a road, not a fun experience. All right, 22, an icy curve they like these icy curves, with a radius of 175 meters is banked at 12 degrees. At what speed do you have to travel to not leave the road? So same question, really. Tan of 12 is equal to v squared over 175 times 9.81. So again, really, this should be a matter of calculator. If you repeatedly get these ones wrong, please check to see that your calculator's in degrees, that you're taking the square root. Those are all really common things that I see. But really, you should just be doing tan of 12, multiply it by 175, multiply it by 9.81, take the square root, and I got 19.1 meters per second. Again, you can always change that into kilometers per hour to figure out kind of in a more realistic sense what that is. Number 23. I saw more than one person with this question as I went through your stuff, so just in case. An engineer has to design a highway curve with a radius of 155 meters, so he knows that has to be the radius of the turn, probably because that's the land that they have available to do that. And it needs to accommodate cars going at a velocity of 85 kilometers per hour. So really the first thing you have to do is you have to change that into meters per second. For some people, that's easier than for other people. So if you have 85 kilometers per hour, again, I would have in 1 kilometer, I would have 1,000 meters. I put the kilometers on the bottom this time so that they would cancel out. And in 1 hour, I have 3,600 seconds. So again, this time I put the hours on top so that they cancel and I have meters per second left. What that turned out to be for me was 23.6 meters per second. So then I just went tan theta is equal to 23.6 squared over 155 times 9.81. So I would figure out what that is. I would do 23.6 squared divided by 155 times 9.81. And then theta would be that shift tan or that arctan or that second function, whatever your calculator says, of whatever that worked out to be. I don't know, I didn't actually write it down in my book. But what I got was that it was 20 degrees. When you're talking about degrees, you don't have to worry about significant figures. Degrees doesn't matter. We usually just round off to the nearest degree. So other than that, I don't really need to do anything else. I just wanted to go over those and confess to you what a stupid teacher you have. I'm sorry. You have a test on Friday. So it'll be at 11. We will do it via Zoom. I will send you the link for that before Friday, so probably on Thursday. You'll probably get that. And so Friday at 11, we'll upload the test. You'll do the test. You'll send it back to me. Life will be good. All right. And then we'll only have a couple of chapters left to do before the end of the year. Woohoo! We're headed into that home stretch. Have a good day.